welcome to Precast Concrete Surveillance. Today I'm joined by the Roads and Maritime Services General Manager of Infrastructure Contracts, Peter Wellings. Now Pete, all of the RMS contracts require quality certified contractors using QA contracts. So why does RMS also undertake surveillance?
Over the last 25 years, where we've been using QA to deliver contracts, we've found that the best results for quality occur when RMS, as we're now known, use surveillance officers and site engineers to surveil contractors, subcontractors and suppliers' works during construction.
Okay, so you purchase large quantities of precast concrete for all aspects of your roads and bridges. I'm guessing sometimes things aren't what they appear at first sight.
Precast concrete may appear perfect when it first arrives on site, but due to poor construction practices and non-compliance with specification, it can have inbuilt defects which are only realised some years after installation. Surveillance ensures that the product is constructed in accordance with our requirements and is a small price to pay for that assurance.
Okay, so we'll be looking into what exactly surveillance involves a little later.
But I must stress that targeted surveillance of precast concrete before and during casting is essential to getting the best possible concrete product for our usage. Our surveillance officers have an extremely important task in ensuring correct quality and one that is essential for all critical concrete components.
Okay, so I guess surveillance is more than having a chat with the precaster.
That's right. Whilst it's important to be polite and treat the precaster staff as professionals, the primary purpose is to minimise RMS risk. Surveillance should be planned and targeted at the high-risk items that are difficult to correct and verify later. Surveillance officers need to give precasters sufficient notice of their intended visit, as well as plan their visit around the relevant work taking place.
You've got to keep on top of them.
Yeah.
Thanks, Pete. Now, in this video, we're going to look at the types of precast concrete, what precast concrete surveillance involves, how to do it, and some of the inside knowledge that you will need that you can't get on the internet. So, joining me now for the rest of the journey is Warren Stalder, Managing Construction Quality for Infrastructure Contracts, who has a wealth of experience in precast concrete. So, Warren, what are the various types of precast concrete?
Well, basically, there are four types of precast concrete that we use. They are precast reinforced concrete, which is reinforced concrete products such as head walls, box culverts, parapet shells and curb units. Precast pre-tension concrete is reinforced concrete where the casting bed has had the pre-stressing wire stressed before casting and includes planks, piles and our most common bridge girders known as the Super Ts. Precast post-tension concrete, where the reinforced concrete is cast with the pre-stressing strand enclosed in ducts and tension after the concrete has reached its required transfer strength and includes I-shaped bridge girders. But because this is not a common means of producing precast members and because it has quite strict and extensive controls, it is not proposed to further cover post-tension concrete here. Then lastly, there is architectural precast concrete, where the concrete is cast with an architectural feature and the finish is required to be of a certain design or pattern. This would include retaining wall panels or noise wall panels. Architectural precast concrete is really a subset of precast reinforced concrete, but has added complications.
Complications to engineers, exciting for architects. Okay, what does precast surveillance involve?
Many of the surveillance activities are common to the various types of precast concrete, but there are additional checks for the pre-stressed concrete and architectural concrete.
Glad to see you looking after the architectural products. So what are the common activities for all precast concrete?
Precast concrete surveillance is best performed using checklists prepared by experienced officers and particularly by staff with construction experience, especially experience in precast concrete. It firstly involves visiting the yard to review the ITPs and WMSs.
Hang on a sec. Now, ITPs and WMSs, we're getting into Star Wars speak here.
ITPs stand for the Inspection and Test Plans and are a checklist used by some precasters to ensure that all of the client requirements have been met. WMSs, or Work Method Statements, detail how the precaster intends to do the work, and from this, an experienced SO can identify likely problems that may occur before any concrete is cast.
Okay, so besides checking the paperwork, what else should she or he do as a surveillance officer?
Well, before any concrete is cast, there are a number of areas to check. Is the concrete batched on site or from a third-party concrete plant? Is it an approved mix as specified on the drawings? Is the mix being used the correct one?
So you mean sometimes the wrong mix can be used?
Absolutely. There have been a few recent cases where the wrong mix or a non-B80 mix was used and not discovered until the pour was half complete, or even worse, until delivered to our site.
Wow. So you don't assume anything?
You need to check all aspects, including the aggregates, admixtures, fly ash, cement, and so on, until you can be confident in the process. Each component has an important part to play in ensuring a durable product, and a mistake in any one can have serious consequences.
Yeah, so the ITP will show what testing arrangements are proposed.
And this needs to be checked so that it conforms.
So we check that the right mix is used, is that it?
Well, not quite. We also need to check that the reinforcing steel and any pre-stressing strand is certified by ACRS and is free from grease, dirt, other contaminants and rust, except that a light surface rust is acceptable. All steel products that have been certified must be visibly labelled for easy identification.
Okay, now tell me, what about welding?
Well, welding of reinforcing steel is not preferred due to the damage that it can do to the steel properties, or even worse, to any adjacent pre-stressing strand, which is a complete no-no. Welding, however, does have advantages, insofar as enabling a very controlled cage to be assembled, which helps ensure that the cover is correct.
Okay. So if it's not preferred, does that mean that where it is used, there are strict conditions?
We need to check that any welding that has an approved procedure, that's the WPQR, and then that the procedure is being followed by the welder. This includes checking that the electrode used is as per the procedure, that the type of weld and the welding amperage is being followed as per the procedure as well. The welder also needs to have been pre-qualified in this type of weld.
Okay, and what about formwork?
Most precast concrete is cast using steel forms. These have a long life, are easily adjusted and released, and produce a superior finish to timber or plywood. But the end product can still be affected by leakages from the joints, gaps in the forms, or rust or other contaminants on the surface.
Geez, there's a lot to think about, isn't there?
Oh, yes.
Okay, so one of the key skills of a surveillance officer is being able to identify likely problems to finish in the forms before casting.
That's correct. And areas to focus on are seals, blockouts, end plates, cast-in anchorages, or anywhere where there is something that varies for each product.
Yeah, so gaps and joints all need to be sealed and tight.
Yes, but sometimes a check also needs to be made that the formwork is correctly aligned with the correct dimensions and level, as forms can move. This may involve getting a survey.
Okay, so now we're getting back to reinforcing. What else needs to be checked?
After the reinforcing cage and any pre-stressing elements are installed, is a good time to visit the yard and check that the mould is completely clean. All of the steel is as shown on the drawings, is installed in the correct location and has the correct cover to the mould and to the surface, and is not fouling any ducts or inserts. It is particularly important to check that the tie wire ends are not in the cover zone.
Okay, so let's get to the yard and see what Warren means. We're at Maxville in northern New South Wales at a living, breathing precasting plant with manager Phil Noakes. What are we looking at, Phil?
Peter, we're looking at a precast facility which has been set up to pour pre-stressed bridge girders and bridge planks. We're currently producing 5 Super Ts for an individual project. So every day we set up and cast 5 Super Ts out of 3 different moulds. We also do bridge parapets, which are just reinforced concrete product, but we've got the capability to do pre-stressed planks as well. So every day you'll see 5 beams which will come out of the mould. We'll then do the setup process. We've got prefabricated reinforcement cages which are already assembled. The mould gets cleaned, it gets oiled up and prepared, any gaps sealed and that, and then the reinforcement cage will get lifted in one piece. We then connect the reinforcement strands, which are already pre-assembled in the bottom of the cages. They're coupled up. We then stress those strands, complete the installation of other bits and pieces into the mould. The product is then, the strand is then stressed to a full stress. We then complete the final checks and processes, and then concrete is placed, and at the end of the day, We'll cover up the beam, we'll heat the beam to provide a curing and accelerated curing process, and overnight that will gain enough strength, so in the morning we'll then release our pre-tension force into the concrete. The beam comes out and we start again.
And then you truck them out of here.
And then we chuck them out. At the moment we're trucking out 6 girders every day.
Wow, I'm excited. Let's have a closer look. Warren, it's great to be out on site, but when you're here, what are you looking for?
Well, when doing a site inspection, you need to make sure that the product has been built as per the design, not just the finish. Make sure there's no honeycombing, make sure all the steel is in the right place, and make sure that the girders are going to meet our design requirements. And each of these Super T girders has a set of drawings that shows where each of the steel reinforcement steel goes and what the cover is.
When we're talking about making concrete products, it's about concrete and about steel. We learn about concrete in the 5 C's of concrete DVD, but the steel's critical.
Absolutely, Peter. The steel has to be in the right location and we have to have the right cover. But more importantly for these products, because they're pre-tension concrete, we need to make sure that the pre-tensioning strand has been correctly stressed. And it's not just important that all the steel is there as per the design, but it's also important that we have the cover to the steel. And then in these products, because they're pre-tension concrete, we need to make sure that the strand is in the correct location and has been stressed to the correct load.
You've got to get this part right.
Absolutely.
Now we're at the actual pre-stressing bay. Warren, what are you looking for here?
Well, first we need to make sure there's been a calculation sheet prepared by a structural engineer which converts the gauge pressure to a strand force but shows the extensions, allowing for any losses.
So Warren, take us through this calculation sheet.
Well, the pressure on the gauge represents the pressure generated by the pump and applied to the jack. The force applied to the strand needs to be calculated and reduced by any friction losses or wedge drawing. This is important due to the need to verify that the correct full force has been applied to the strand, as this determines the strength of the Super T or any other pre-tension product. This calculation sheet needs to use the Young's modulus applicable to that particular coil, and hence the coil number needs to be known and have a Young's modulus recorded. The pump's gauges also need to be in current calibration, that is within the last 6 months with the jack, and the maximum jacking force should be between 50% and 90% of the gauge capacity.
So wedges draw in barrels. What is this about?
Well, at the end of each strand, there's a pair of wedges which locks the strand into a barrel and prevents the strand from releasing its load. The specification has a limit on the tolerance of drawing from the design of plus or minus 2 millimetres.
So it's what we're seeing here.
That's correct.
Yeah. Is this something you need to check, that tolerance?
This needs to be checked periodically. Peter, wedges can wear, and if they're not replaced, they can increase their drawing, which affects the residual load from the design in the strand. Now, we need to ensure that no more than 80% of the minimum braking force of the strand is applied to the jack at any time. The primary means of verifying the force is through the pump gauge pressure. Gauges should be able to be read to the nearest 0.5 MPa. There should be 2 gauges, which should give the same reading. Now, when we see here is only 1 gauge, because this is just the initial take-up of the strand, so normally you'll have 2 gauges. The actual gauge pressure should be within plus or minus 2.5% of the calculated pressure.
How would you check the force in the strand?
Well, that's a good question, Peter. But the force in the strand is actually checked by measurement of the extensions of a selection of strands. This calculated extension will be shown on the extension calculation sheet. All of this needs to be recorded on the record sheet as part of the product's records.
It's a cross-check system, isn't it?
That's correct. A check of the force is indicated by the pressure gauges against the actual force causing the extension.
Okay. Let's run through again how we ensure that the correct force is applied to the strands.
Well, there needs to be a calculation sheet completed and signed by a structural engineer. All relevant losses need to be allowed for, and we've got to make sure that the coil number being used relates to the calculation sheet. The gauges need to be calibrated within the last 6 months, a minimum of 150 millimetres diameter and read to 0.5 MPa. The maximum drawing must be within plus or minus 2 millimetres of the calculated drawing,
and the force on the strand must never exceed 80% of the minimum breaking force of the strand. And lastly, the pressure needs to be within 2.5% of the calculated pressure.
That is all well and good if everything is going to plan, but what happens if the actual extension is different from the calculated extension?
With pre-tension concrete, this is generally less common, and if it does occur, it's more likely due to a calculation being different to the actual parameters. If the measured extension differs from the calculated extension by more than, say, 3% at any stage, then you should stop the pre-stressing and the cause for the difference determined and take steps in accordance with the relevant specification.
And if there's still some doubt?
Well, if there's still some doubt, then an experienced bridge design engineer from Roads and Maritime Services should be consulted.
Warren, the plant's now really gearing up for the concrete pour. What have they checked?
Well, they've checked the cover and they've checked that they've got internal vibrators. But in this place, because they use form vibrators mainly for compaction, you can obviously hear that there is plenty of vibration happening.
If you've never been on the site before, this is where you really have to have your wits about you to hear yourself think. I reckon we should get out of here so we can talk properly.
Absolutely.
Well, that noise can be deafening during the concrete pour. But during the pour, what is the role of the surveillance officer?
Well, the role of the surveillance officer is quite limited. Just prior to the pour, he or she will check that they're using the correct mix, that the truck dockets are within the specification time and showing the correct mix, as well that the slump is correct. If high slump mixes are used, then the use of a traditional slump cone can be rather meaningless, and better use is made of a flow board to determine the slump.
Okay, so Warren, what are some of the problems here we need to look out for?
Well, this facility has been designed to enable the products to be concreted from the back of an agitator chute, and thus there are none of the problems associated with pumps. One particular problem with products such as Super Tees is ensuring that the concrete flows and is compacted completely underneath that internal mould. Each precaster will develop a system to ensure that this happens and will rely on a set method for concrete placement followed by a pattern of turning on and off the external form vibrators. And because of the large forces involved in the compaction of these products, it is essential that the bar chairs used for support do not collapse or move. Concrete aspirators are a proven support, but can be unsightly in exposed circumstances. Otherwise, approved plastic chairs are also acceptable. One unlikely potential problem can be cold joints if there is not a continuous supply of concrete. Extremes of temperature are not so pronounced with precast concrete due to the facilities usually being underneath a covered area such as here. B80 has more relaxed temperature limits for precast concrete, but this still must be controlled. Another problem that can occur with products such as planks is preventing the void formers from floating, as well as getting all of the concrete compacted beneath the voids. And lastly, perhaps the biggest potential issue and the site of most repairs is ensuring that the concrete fills and is compacted around the product's congested ends. This may mean the use of a smaller sized aggregate in the mix, as well as pencil vibrators in addition to the normal vibrators.
So, after concreting, what comes next? I'm guessing curing.
Yes, you're right. All concrete products are required to be cured. In order to maximise the number of products produced from a mould, most precast facilities will opt to use heat accelerated or sometimes steam curing to enable early release from the mould. There are strict requirements in our specification B80 to control both forms of curing. Now, this is because this form of curing has the potential to cause cracking damage to the product or cause a phenomenon known as delayed etronite formation, or DEF, which happens later in the product's life. DEF will expand and destroy the concrete as a protective member for reinforcement steel. DEF occurs when the curing temperature exceeds around 70 degrees C and other factors such as moisture are present. Hence, there are general limits in B80 about heat accelerated or steam curing.
Heat accelerated curing seems to be a high risk item. Let's run through the principles of that.
Well, the concrete needs to be allowed to gain some strength before commencing of the curing regime, and hence there needs to be a minimum 2 hours before commencement of steam curing or heat accelerated curing, or the maturity must be 50 degrees C hours, but a maximum of 5 hours. The concrete must be kept wet with relative humidity exceeding 98% during the process to prevent drying shrinkage. The rate of temperature gain must be limited to 24 degrees C per hour to prevent too rapid heat gain. The maximum temperature needs to be kept to 70 degrees C for all exposure classifications. Now, in order to prevent shock loads to the concrete, the covers cannot be removed or work on the member until the temperature is within 40 degrees C of ambient. The temperature must be continuously recorded with a thermograph.
So Warren, after the concrete's poured and cured, what's left?
Well, we then need to release the pre-stressing force from the strand into the concrete. In this factory, that's done by using the multi-head jack, which moves forward and gradually releases the force into the concrete.
That's not always the case.
No, that's correct, Peter. It's probably more common that the strand is released using annealing or gradually heating of the strand to allow the load to be gently transferred into the concrete. The transfer strength of the concrete can be found in the drawings, and you cannot release the strand until that transfer strength has been achieved. Release of the strand should be a gradual process. Use a flame torch and allow the transfer of the load from each strand into the concrete. Now, we're not using that process here, but in a factory which does use that, you must make sure that the flame does not go closer than 5 millimetres to the concrete. And B110 states that any minor spalling due to that release can be repaired without generating an NCR.
So what happens now after all the strands have been released?
Well, after all the strands have been released, then the ends of the members can be tidied up using an angle grinder and an epoxy or an epoxy mortar to protect the ends of the strand. B110 provides more details on this.
So is that it for pre-tension members?
Almost. We need to make sure the product is not only dimensionally conforming, but also that the required standard of surface finish. For the first members produced out of a mould, this will involve a dimensional check as per B110. And for all members, you need to visually check that there's no honeycombing, cracking or spalling before it leaves the factory. Any minor repairs can be made with concrete and a wet to dry epoxy primer. It's also important to ensure that the members are not damaged during transport or handling. Concrete, which has gained its strength quickly, is susceptible to spalling. Thus, the product must be allowed 7 days storage time before transporting. B110 has various requirements for storage, which need to be complied with.
Now we've looked at precast pre-tension concrete panels. Oh, Warren, I believe there's precast architectural panels as well.
Absolutely, Peter. And Roads and Maritime Services has extensive experience in ordering precast architectural concrete. And actually, it's won numerous awards for the quality of the designs produced.
Well, what's the difference with architectural concrete?
Well, it's important that agreement is reached early with the architect as to the design, the finish, and what can be achieved repeatedly in a precast concrete factory. Then the first step is to prepare a reference panel, which is accepted by both the architect as an acceptable result and by the precaster as achievable. Sufficient time needs to be allowed for agreement to be reached. The panel must be preserved until the works are completed.
So what else needs to be considered for architectural concrete?
The ability to undertake repairs on architectural concrete will often be severely limited due to the effect that the repairs will have on the finish. Thus, defects may mean that more product is rejected than would normally occur.
Warren, are there any aspects where this is more likely the case?
Well, particular finishes such as exposed aggregate are in themselves highly variable, and this is due to their process and the variability of the operation.
Well, Warren, I can't believe I'm saying this, but most of these things you'd see whizzing past at 100 k an hour.
Well, that's true, Peter, and some latitude should be given to precast factories, especially when it comes to minor differences in texture. However, at other times, the finish is important as it forms a key part of an urban design outcome. And in these instances, a tighter acceptance criteria may need to be applied.
So, Warren, again, what are the key points for architectural concrete?
Well, I think you need to allow sufficient time for approval. Always construct a reference panel and keep it until the project is complete. Appreciate that there's inherent variability of some finishes and apply common sense when determining acceptance criteria. Understand the process and the limitations of repeatability of some types of precast concrete, such as exposed aggregate.
That was an amazing day on site. I learned so much. Well, that brings us to the end of precast concrete surveillance. Precast concrete has many advantages for quality projects due to the tight control available over the process. But in order to ensure that these controls are applied targeted surveillance is essential. Although it sounds like there's a lot involved in precast concrete, the key is to understand the process and refer to the relevant specification, and if in doubt, always ask someone who knows.